Gazing up at the night sky, we often find solace in the familiar glow of the moon. It has been a constant companion to Earth for billions of years, its gentle light illuminating our nights and inspiring countless myths and legends. But what if we told you that this celestial ballet, this cosmic dance between our planet and its moon, is slowly changing? What if we told you that the moon is, ever so slowly, drifting away from us? It's a thought that might seem ripped from the pages of science fiction, a slow-burning cosmic drama unfolding over eons. Yet this is not a figment of imagination, it's a scientific reality. The moon, our celestial neighbor, the very object that has shaped our planet's tides, influenced the length of our days, and even played a role in the evolution of life itself, is embarking on a journey that will see it gradually recede from our grasp. This isn't a sudden cataclysmic event, but a slow, almost imperceptible drift. The moon is moving away from Earth at a rate of about 3.8 centimeters per year, roughly the width of a golf ball. While this may seem insignificant on a human timescale, over millions and billions of years, this subtle movement adds up, painting a picture of a future where the Earth-Moon relationship will be vastly different from what it is today. But why is this happening? What unseen forces are driving our celestial companion away? The answer lies in a fascinating interplay of gravity, energy, and the very fabric of space-time itself. Join us as we delve into the science behind this celestial phenomenon, exploring the hows, the whys, and the implications of the moon's slow farewell. To understand the moon's gradual retreat, we must first turn our attention to an invisible force that governs the cosmos: gravity. Gravity, the force that holds us to the Earth and dictates the motion of planets around stars, is also responsible for the intricate dance between the Earth and the moon. It's not just a simple matter of one pulling on the other, it's a complex interplay that creates a cosmic tug-of-war with far-reaching consequences. One of the most visible manifestations of this gravitational interplay is the phenomenon of tides. The moon's gravitational pull tugs on the Earth's oceans, causing them to bulge out on the side facing the moon, and surprisingly, on the opposite side as well. These bulges are what we experience as high tides, while the areas between them experience low tides. This rhythmic rise and fall of ocean levels are a constant reminder of the moon's powerful influence on our planet. However, the story doesn't end there. The Earth, in its constant rotation, doesn't align perfectly with these tidal bulges. The Earth spins faster than the moon orbits, causing these bulges to be slightly ahead of the moon's orbit. This misalignment creates a sort of gravitational push on the moon, transferring energy from the Earth's rotation to the moon's orbit. This energy transfer, while incredibly slow, has a profound effect over vast stretches of time. It's like gently pushing a swing. Each push might be small, but over time it causes the swing to go higher and higher. Similarly, the gravitational nudge from the Earth's misaligned tidal bulges slowly but surely pushes the moon into a slightly higher, wider orbit, causing it to drift further away with each passing year. The idea of the moon slowly spiraling away from Earth might seem like a concept confined to the realm of science fiction, but the evidence for lunar drift is firmly rooted in scientific observation and measurement. Scientists have been able to track the moon's movement with incredible precision, confirming that it is indeed moving away from us at a rate of approximately 3.8 centimeters per year. This measurement isn't based on guesswork or speculation, it's the result of sophisticated technology and meticulous observation. Using lasers and reflectors placed on the moon's surface during the Apollo missions, scientists can bounce laser beams off these reflectors and measure the time it takes for the light to return to Earth. These measurements, accurate to within millimeters, provide irrefutable proof of the moon's slow but steady retreat. But the evidence for lunar drift isn't limited to modern technology. By studying geological formations and analyzing ancient sediments, scientists can piece together a history of the Earth-Moon system stretching back billions of years. These studies reveal that the moon was indeed much closer to Earth in the distant past, confirming that lunar drift is not a recent phenomenon, but a process that has been shaping our planet for eons. This journey back in time, piecing together the history of the Earth-Moon relationship, allows us to appreciate the profound impact this slow drift has had on our planet. It has shaped our tides, influenced the length of our days, and even played a role in the evolution of life itself. Understanding lunar drift isn't just an exercise in abstract astrophysics, it's about unraveling the story of our planet and the celestial dance that has shaped us. The moon's slow drift away from Earth is more than just a curious astronomical phenomenon, it's a testament to the dynamic and ever-changing nature of the cosmos. It reminds us that even the seemingly immutable heavens are in a constant state of flux, with forces operating over timescales that dwarf human comprehension. As we continue to study the moon's journey, we are constantly reminded of the interconnectedness of celestial bodies and the subtle ways in which they influence one another. The moon's gravitational pull, responsible for driving its own retreat, also plays a vital role in stabilizing Earth's axial tilt, which in turn governs our planet's seasons. The moon's influence extends beyond our planet's physical processes. It has also shaped our culture, inspiring countless myths, legends, and artistic expressions. From ancient lunar calendars to modern space exploration, the moon has captivated the human imagination for millennia, serving as a symbol of wonder, mystery, and the vastness of the universe. As we delve deeper into the science of lunar drift, we embark on a journey of discovery that transcends the boundaries of our own planet. It's a journey that takes us to the heart of the cosmos, revealing the intricate workings of gravity, the dance of celestial bodies, and the profound interconnectedness of all things in the universe. Join us as we continue to explore the mysteries of our celestial partner and unravel the secrets hidden within the moon's slow farewell. Imagine a cosmic dance floor where the Earth and the moon waltz through the vastness of space, bound together by an invisible force gravity. This gravitational embrace, however, is not a static embrace. It's a dynamic interplay that creates a constant tug-of-war between our planet and its celestial partner. And just like in any good dance, this cosmic tango has its own set of steps, each movement influencing the other in a delicate balance of push and pull. The moon's gravity, though weaker than Earth's, is strong enough to exert a noticeable pull on our planet. This pull is most evident in the oceans, where the moon's gravity tugs on the water, causing it to bulge outward on the side facing the moon. What's even more fascinating is that a similar bulge occurs on the opposite side of the Earth, as if the oceans are being stretched like a rubber band around our planet. These bulges, of course, are what we experience as high tides, while the areas between them experience low tides. This tidal tug-of-war doesn't end with the oceans. It also affects the solid Earth itself, although to a much lesser extent. The Earth's crust and mantle deform slightly under the moon's gravitational pull, creating a subtle bulge that follows the moon's orbit. This phenomenon, known as Earth tides, demonstrates that even the seemingly solid ground beneath our feet is subject to the moon's influence. However, this gravitational dance is far from harmonious. The Earth, in its relentless rotation, spins faster than the moon orbits our planet. This difference in speed creates a crucial misalignment between the Earth's rotation and the tidal bulges created by the moon's pull. This misalignment, as we'll discover, is the key to understanding why the moon is slowly but surely escaping Earth's gravitational grasp. Imagine the Earth's oceans, vast and deep, responding to the moon's gravitational beckoning like a dancer following their partner's lead. As the moon orbits our planet, its gravity tugs on the water, creating bulges that rise and fall in a rhythmic dance that has shaped coastlines and influenced life on Earth for billions of years. These bulges, known as tides, are a testament to the invisible forces that govern our universe, a cosmic ballet played out on a planetary scale. The most pronounced tidal bulges occur on the sides of Earth facing directly towards and away from the moon. This is because the moon's gravity is strongest at these points, pulling the water towards it on one side and, counterintuitively, stretching the Earth away from the water on the opposite side. These bulges create high tides, while the areas between them, where the water is drawn away towards the bulges, experience low tides. But the story of tides is not as simple as just two bulges following the moon's orbit. The Earth's rotation, the continents, and even the ocean floor itself all contribute to the complex patterns of tides we observe around the globe. The Earth's rotation, for example, causes the tidal bulges to be slightly ahead of the moon's orbit, like a dancer stepping slightly ahead of their partner. These tidal bulges, while essential to the Earth-Moon system's delicate balance, are also at the heart of the Moon's slow escape. The misalignment between the Earth's rotation and the tidal bulges creates a gravitational push on the Moon, transferring energy from the Earth's rotation to the Moon's orbit. It's this subtle transfer of energy acting over eons that is slowly nudging our celestial companion further away. Imagine two dancers, perfectly synchronized, gliding effortlessly across the dance floor. Now, imagine one dancer slightly out of step, their movements subtly disrupting the flow. This is analogous to the relationship between the Earth's rotation and the tidal bulges created by the Moon's gravity. The Earth, spinning slightly faster than the Moon orbits, creates a misalignment that, while seemingly insignificant, has profound consequences over cosmic timescales. As the Earth rotates, it carries the tidal bulges with it, but these bulges are slightly ahead of the Moon's orbit due to the Earth's faster rotation. This misalignment means that the gravitational pull of these bulges isn't perfectly aligned with the Moon's orbit. Instead, it exerts a slight tug on the Moon, pulling it slightly forward in its orbit. This gravitational tug, though minuscule, has the effect of transferring energy from the Earth's rotation to the Moon's orbit. It's like gently pushing a child on a swing. Each push might be small, but over time, they add up, causing the child to swing higher and higher. Similarly, the Earth's rotational energy is slowly but surely being transferred to the Moon, causing it to spiral outward into a slightly higher, wider orbit. This process, known as tidal acceleration, is the driving force behind the Moon's slow drift away from Earth. It's a subtle dance of gravity in motion, a cosmic ballet where a slight misalignment creates a force that, over eons, reshapes the very fabric of the Earth-Moon system. The notion that the Moon is drifting away from us might seem like a fantastical tale, a story spun from the threads of imagination rather than scientific fact. Yet the evidence for this celestial separation is irrefutable, meticulously gathered through decades of meticulous observation and technological ingenuity. Scientists, armed with lasers, reflectors, and a deep understanding of celestial mechanics, have not only confirmed the Moon's retreat, but have also measured its pace with astonishing accuracy. One of the most remarkable feats of modern astronomy is the ability to measure the distance to the Moon with pinpoint precision. This is achieved using a technique called lunar laser ranging, which relies on retroreflectors placed on the Moon's surface during the Apollo missions and by unmanned Soviet rovers. These retroreflectors are essentially mirrors designed to reflect light back towards its source, regardless of the angle of incidence. By firing powerful laser beams from observatories on Earth towards these lunar retroreflectors and measuring the time it takes for the light to return, scientists can calculate the distance between the Earth and the Moon with an accuracy of a few millimeters. These measurements, repeated over decades, have provided irrefutable proof that the Moon is indeed moving away from us at a rate of approximately 3.8 centimeters per year. This might seem like an incredibly small distance, barely noticeable on a human scale. However, over vast stretches of geologic time, this seemingly insignificant movement adds up, painting a picture of a dynamic Earth-Moon system where distances shift, orbits evolve, and the celestial dance continues to unfold in ways that both captivate and challenge our understanding of the cosmos. The Moon's slow drift away from Earth, though measured in mere centimeters per year, is not without its consequences. Over vast stretches of geologic time, this seemingly insignificant movement will have a profound impact on our planet, influencing everything from the length of our days to the stability of our planet's axis. Understanding these long-term consequences is crucial for comprehending the intricate relationship between Earth and its celestial companion. One of the most direct effects of the Moon's retreat is the gradual slowing down of Earth's rotation. As the Moon moves further away, the gravitational tug-of-war between the two bodies weakens slightly. This, in turn, causes the Earth's rotation to slow down, ever so gradually lengthening our days. Don't worry though, we're not talking about drastic changes overnight. The lengthening of our days is happening at a rate of about 1.7 milliseconds per century. While this might seem inconsequential, over millions of years this gradual lengthening of our days will add up. In the distant future, a day on Earth will be significantly longer than the 24 hours we're accustomed to. This change in the length of our days will have a ripple effect on our planet's environment, influencing everything from the rhythms of nature to the way we measure time itself. The moon's retreat will also affect the stability of Earth's axial tilt. The Earth's axial tilt, the angle at which our planet is tilted on its axis, is what gives us our seasons. The moon's gravity plays a crucial role in stabilizing this tilt, preventing drastic wobbles that could lead to extreme climate change. As the moon moves further away, its stabilizing influence weakens, potentially making Earth's axial tilt more susceptible to wobbles caused by the gravitational pull of other planets in our solar system. Gazing into the cosmos is akin to peering through a window into the depths of time. As we study the celestial ballet of the Earth-Moon system, we're not just observing the present, we're witnessing the culmination of billions of years of cosmic evolution, a slow and majestic dance governed by the laws of physics and the subtle interplay of gravity. Deciphering the future of this celestial partnership requires unraveling the cosmic clock, understanding how the moon's slow retreat will shape the destiny of both bodies. As the moon continues to drift away, the gravitational tug-of-war between our planet and its celestial companion will gradually weaken. This will lead to a point, billions of years in the future, where the moon's orbit stabilizes and its outward journey comes to an end. At this point, the Earth and the moon will be locked in a gravitational embrace, their rotations synchronized, with the same side of the moon always facing Earth. However, the story doesn't necessarily end there. The fate of the Earth-Moon system is also intertwined with the evolution of our Sun. As the Sun ages, it will eventually enter its red giant phase, expanding outwards and engulfing the inner planets, including Earth. Whether the moon will escape this fiery demise or be consumed along with its celestial partner remains an open question, a tantalizing mystery that future generations of astronomers will strive to solve. The moon's slow drift away from Earth is a poignant reminder of the impermanence of even the most seemingly eternal celestial arrangements. It highlights the dynamic nature of our universe, a cosmic dance where even the smallest of movements can have profound consequences over eons. As we continue to study this celestial ballet, we gain a deeper appreciation for the intricate workings of our cosmos and the interconnectedness of all things in the grand tapestry of space and time. To truly grasp the significance of the moon's slow drift away from Earth, we must embark on a journey through time, rewinding the cosmic clock billions of years to a period when our planet was still in its fiery infancy. It was during this tumultuous epoch that the moon, our faithful celestial companion, was born, and the intricate dance of lunar drift began its subtle but relentless choreography. The prevailing scientific theory suggests that the moon formed as a result of a colossal cosmic collision between the early Earth and a Mars-sized object referred to as Theia. This cataclysmic impact, occurring roughly 4.5 billion years ago, ejected a tremendous amount of debris into Earth's orbit, forming a swirling disk of molten rock and dust. Over time, this debris coalesced under the relentless pull of gravity, eventually giving birth to the moon. In the aftermath of this cosmic clash, the newborn moon was much closer to Earth than it is today, perhaps as close as 22,000 kilometers, a mere stone's throw on a cosmic scale. At this close proximity, the gravitational interaction between Earth and the moon was significantly stronger than what we experience today, shaping our planet in ways we are only beginning to understand. This close embrace marked the beginning of the moon's slow but inexorable drift away from Earth. The same tidal forces that govern our oceans today were at play in this early Earth-Moon system, although their effects were far more dramatic and far-reaching. The stage was set for a billion-year dance, a slow and subtle waltz between two celestial bodies, each movement leaving an indelible mark on the other. Imagine a young Earth still reeling from the colossal impact that birthed the moon, its surface a churning sea of molten rock. Towering above this fiery landscape, the newly formed moon, larger and brighter than it appears today, exerted a gravitational pull far exceeding what we experience in modern times. This close proximity created a world of tidal extremes, where the very fabric of our planet responded to the moon's gravitational embrace. The tides on this early Earth were not merely a gentle rise and fall of ocean levels, they were colossal bulges of molten rock, stretching kilometers high and sweeping across the planet's surface in a relentless rhythmic dance dictated by the moon's gravitational pull. These massive tidal forces generated intense friction within the Earth's interior, heating the planet's core and contributing to the volcanic activity that shaped our planet's early crust. The oceans too responded to this amplified lunar pull, experiencing tides of unimaginable scale. Imagine coastlines redrawn daily as colossal waves driven by the moon's gravity crashed onto shores and receded, leaving behind a landscape sculpted by the relentless ebb and flow of a tidal force far exceeding anything we witness today. This period of tidal extremes played a crucial role in shaping the early Earth, influencing the distribution of heat within our planet, driving volcanic activity, and contributing to the formation of the first continents. It was a time of dramatic change, a cosmic ballet where the moon's gravity orchestrated the evolution of our planet. As the young Earth cooled and solidified, the moon's gravitational influence extended beyond simply shaping the planet's physical features. It also played a crucial role in establishing the conditions necessary for life to emerge. The massive tides generated by the moon's proximity churned the primordial oceans, creating a dynamic environment rich in chemical nutrients essential for the formation of the first organic molecules. Furthermore, the moon's gravitational pull helped to stabilize Earth's axial tilt, preventing wild fluctuations that could have led to extreme and unstable climates. This stabilizing influence was crucial for the development and evolution of early life forms, which were highly sensitive to changes in temperature and the availability of sunlight. The moon's presence also influenced the length of Earth's day. Billions of years ago, an Earth day was significantly shorter, perhaps lasting only a few hours. The moon's gravitational pull, acting as a brake on Earth's rotation, gradually slowed down our planet's spin, eventually leading to the 24-hour day we experience today. This lengthening of the day had a profound impact on the evolution of life, influencing the development of circadian rhythms and the cycle of day and night that governs so much of life on Earth. The early Earth-Moon system was a dynamic and interconnected duo, their fates intertwined from the very beginning. The moon's presence was not merely that of a passive observer, it was an active participant in shaping the destiny of our planet, influencing its physical features, its climate, and ultimately the very emergence of life itself. While the moon's influence on Earth has been profound, its distance from our planet has not remained constant. Over billions of years, the moon has been steadily receding from Earth, its orbit widening at a rate that, while incredibly slow, has resulted in a significant change in the Earth-Moon dynamic. Charting this gradual retreat is like piecing together a cosmic puzzle, using a combination of geological evidence, astronomical observations, and sophisticated computer models. One of the key pieces of evidence for the moon's retreat comes from the study of tidal rhythmites, ancient sedimentary rocks that preserve a record of tidal cycles from millions and even billions of years ago. By analyzing the thickness and composition of these layers, scientists can reconstruct the frequency and intensity of past tides, providing valuable clues about the moon's distance from Earth at the time these sediments were deposited. Another line of evidence comes from lunar laser ranging, a technique that uses lasers to measure the distance to the moon with incredible precision. By bouncing laser beams off reflectors placed on the moon's surface during the Apollo missions, scientists can track the moon's movement with millimeter accuracy, confirming its slow but steady retreat from Earth. These observations, combined with sophisticated computer models that simulate the long-term evolution of the Earth-Moon system, have allowed scientists to reconstruct the history of the moon's drift with remarkable detail. These reconstructions reveal that the moon has been steadily receding from Earth throughout its history, its orbit widening at an average rate of about 3.8 centimeters per year. Imagine walking along a rocky coastline, the wind whipping through your hair as you gaze out at the vast expanse of the ocean. Now imagine that the rocks beneath your feet hold within them a record of ancient tides, a testament to the moon's gravitational pull stretching back millions, even billions of years. These rocks, known as tidal rhythmites, offer a fascinating glimpse into the distant past, allowing scientists to reconstruct the history of the Earth-Moon system and track the moon's slow retreat through time. Tidal rhythmites are sedimentary rocks formed by the rhythmic deposition of sediments in coastal environments influenced by tides. As tides rise and fall, they carry with them varying amounts of sediment, which settle out in distinct layers. Over time, these layers accumulate, creating a layered rock formation that reflects the cyclical nature of the tides. The thickness and composition of these layers provide valuable clues about the height, frequency, and energy of the tides that form them. By studying tidal rhythmites from different geological periods, scientists can track how the moon's distance from Earth has changed over time. For example, tidal rhythmites from the early Earth, when the moon was much closer, show evidence of much higher and more frequent tides than those observed today. As we move forward in geological time, the layers in tidal rhythmites reveal a gradual decrease in tidal height and frequency, reflecting the moon's slow but steady retreat. These ancient rocks, silent witnesses to the ebb and flow of time, provide tangible evidence of the moon's influence on our planet. They serve as a reminder that the Earth-Moon system is not static but is constantly evolving, with each celestial dance leaving an indelible mark on the geological record. The moon's slow drift away from Earth has been a subtle but persistent force shaping our planet's history. It's a story of interconnectedness, of cause and effect playing out over vast stretches of geological time, leaving its mark on everything from the length of our days to the evolution of life itself. Understanding this interconnectedness is crucial for comprehending the delicate balance that has allowed life to flourish on our planet. As the moon has gradually receded, its gravitational pull on Earth has weakened, causing our planet's rotation to slow down. This gradual slowing of Earth's rotation has led to a lengthening of our days. Billions of years ago, an Earth day was significantly shorter, perhaps lasting only a few hours. Over time, the moon's gravitational braking effect has lengthened our days to the 24 hours we are familiar with today. This lengthening of the day has had a profound impact on the evolution of life on Earth. Organisms have evolved biological clocks, known as circadian rhythms, that are synchronized to the 24-hour cycle of day and night. These rhythms influence everything from sleep-wake patterns to hormone production. Without the moon's influence, Earth's rotation would be much faster, and the day-night cycle would be significantly shorter, potentially impacting the evolution of life as we know it. Furthermore, the moon's gravitational pull has played a crucial role in stabilizing Earth's axial tilt, preventing wild fluctuations that could have led to extreme and unstable climates. This stability has been essential for the development and evolution of life, which thrives in environments with relatively stable climates. As the moon continues to drift away, its stabilizing influence will gradually weaken, potentially making Earth's climate more susceptible to change in the distant future. The story of the moon's drift away from Earth is a testament to the dynamism of our universe, a reminder that even the seemingly immutable heavens are in a constant state of flux. As we trace the moon's journey from its fiery birth to its current position, we gain a profound appreciation for the intricate interplay of gravity, time, and the evolution of celestial bodies. Looking back through billions of years, we see a moon that has played a pivotal role in shaping the Earth we know today. Its gravitational pull has sculpted our planet's features, influenced its rotation, stabilized its axial tilt, and even played a role in the emergence of life itself. The moon's story is inextricably linked to our own, a cosmic partnership that has shaped the course of life on Earth. As we look to the future, we know that the moon's journey will continue, its orbit slowly widening as it gradually recedes from our planet. While this drift is incredibly slow, its effects will become more pronounced over vast stretches of time. The length of our days will continue to increase, the stability of Earth's axial tilt may be compromised, and the tides will gradually weaken. The moon's slow farewell is a reminder that the cosmos is a dynamic and ever-changing place, where even the most seemingly eternal arrangements are subject to the relentless march of time. As we continue to study this celestial dance, we gain a deeper understanding of our place in the universe and the intricate web of connections that bind us to our celestial neighbors. The story of lunar drift is far from over. It is an ongoing saga of cosmic evolution, a testament to the dynamism and wonder of our universe. The moon's gravitational pull, the invisible tether that connects our planet to its celestial companion, is most tangibly felt in the rhythmic rise and fall of our oceans, the tides. This daily dance of water, driven by the moon's pull, has shaped coastlines, influenced marine ecosystems, and even played a role in human history, guiding maritime exploration and shaping coastal communities. However, as the moon continues its slow drift away from Earth, the strength of its gravitational embrace weakens, leading to subtle but significant changes in the tides that will reshape our planet's coasts over eons. The most immediate consequence of the moon's retreat is a gradual weakening of tidal forces. As the moon's gravitational pull diminishes, the difference between high and low tides will decrease, resulting in less dramatic tidal ranges. Coastlines that once experienced vast expanses of exposed seabed during low tides will see these areas shrink, while areas accustomed to towering high tides may experience less extreme fluctuations in water levels. These seemingly subtle shifts in tidal patterns will have cascading effects on coastal ecosystems. Intertidal zones, those dynamic areas of the coastline that are submerged during high tides and exposed during low tides, are home to a rich diversity of life, specially adapted to survive in these fluctuating conditions. As tidal ranges decrease, the boundaries of these intertidal zones will shift, potentially squeezing out certain species and altering the delicate balance of these ecosystems. The moon's retreating influence will also impact the way waves interact with coastlines. Tidal currents, driven by the moon's pull, play a significant role in shaping coastal erosion and sediment transport. As tidal forces weaken, these currents will become less powerful, potentially leading to changes in erosion patterns, sediment deposition, and the overall morphology of coastlines. Beaches may grow or shrink, inlets may close or widen, and the very shape of our continents will be subtly but inevitably altered over vast stretches of geological time. Our perception of time is tied to Earth's rotation. The 24-hour cycle from sun to moon is a constant we take for granted. However, the moon's slow retreat is causing Earth's rotation to gradually slow. Scientists have determined that the length of an Earth day is increasing by approximately 1.7 milliseconds per century. Over millions of years, these milliseconds add up, leading to significantly longer days. This gradual lengthening will have far-reaching consequences for life on Earth. Biological clocks, synchronized to the 24-hour cycle, will need to adapt. Earth's axial tilt at approximately 23.5 degrees gives us our seasons. This tilt is influenced by the moon's gravitational pull, which stabilizes Earth's spin. As the moon drifts away, its stabilizing influence weakens. Without the moon's steadying hand, Earth's axial tilt could vary more dramatically. These variations could lead to more extreme climate changes. Imagine longer periods of extreme heat or cold, more intense storms, and dramatic shifts in weather patterns. The moon's influence on Earth's stability is profound. Life on Earth has evolved in concert with celestial rhythms. The moon's influence is seen in the synchronization of reproductive cycles with lunar phases. Many marine organisms release their eggs and sperm in synchrony with specific phases of the moon. Beyond the marine realm, the moon's influence can be seen in the behavior of nocturnal animals. Even humans are not immune to the moon's subtle influence, with sleep-wake cycles affected by moonlight. The moon's cycles influence activity patterns, hunting strategies, and social interactions. In the distant future, the moon will hang more distant in the sky. This drift will reshape Earth, altering coastlines and lengthening days. Coastal communities will need to adapt to changing coastlines and altered tidal patterns. The lengthening of Earth's days will pose challenges for biological clocks. Organisms will need to adapt to longer periods of daylight and darkness. Understanding gravitational forces within our solar system will be crucial for mitigating potential disruptions. The moon's slow drift away from Earth is a reminder of the dynamic nature of our universe. It underscores the interconnectedness of celestial bodies and the profound influence of cosmic interactions. The Earth-Moon system is revealed to be a dynamic duo, engaged in an intricate dance. By studying the moon's slow farewell, we gain a deeper appreciation for the interconnectedness of all things in the universe. It is a story that inspires awe and humility, reminding us of our place in the grand scheme of cosmic evolution. The moon's retreat, approximately 3.8 centimeters per year, will continue for billions of years. Imagine a future where each generation inherits a slightly more distant moon. This gradual retreat will eventually reach a point of equilibrium. The Earth-Moon system is bound by a complex interplay of gravitational forces. The evolution of our Sun will also play a significant role in shaping the destiny of both bodies. As the Sun ages, it will undergo dramatic transformations, altering the gravitational landscape of our solar system. These changes will influence the fate of the Earth-Moon system. The moon's outward migration will eventually reach a point of equilibrium. The gravitational pull between Earth and the moon weakens with distance. Scientists estimate that this point will be reached when the moon is approximately 1.6 times its current distance from Earth. At this distance, the Earth's rotation will have slowed significantly. The moon will be tidally locked to Earth, meaning that the same side of the moon will always face our planet. The Earth-Moon system will still be influenced by the gravitational pull of other celestial bodies. The possibility of the moon breaking free from Earth's gravitational embrace is improbable, but not impossible. The future of the Earth-Moon system is governed by the evolving dynamics of our solar system. Gravitational tugs from planets like Jupiter could potentially nudge the moon towards a path that leads away from Earth. The evolution of our Sun could also provide an opportunity for the moon to escape Earth's gravitational grip. However, these scenarios are highly unlikely. The Earth-Moon system has maintained its delicate balance for billions of years. The moon's presence has been a constant throughout human history. The most immediate consequence of the moon's absence would be the disappearance of tides as we know them. Without the moon's rhythmic tug, the oceans would redistribute, resulting in much smaller tidal ranges. The absence of the moon's gravitational influence would also impact Earth's rotation and axial tilt. These wobbles could result in more extreme and unpredictable climate variations. The night sky would be forever altered, with the moon's familiar glow replaced by a darker, starrier expanse. An Earth without the moon would be a profoundly different place, its rhythms altered, and its future uncertain. As we contemplate the future of the moon, its slow drift away from Earth, and the potential implications for our planet, we are reminded that the cosmos is a realm of constant change, where even the most seemingly eternal arrangements are subject to the relentless march of time. The moon's journey, a celestial ballet choreographed by the laws of physics, is a testament to this dynamism, a reminder that the universe is not static, but rather a tapestry of interconnected events unfolding across vast stretches of time and space. While the moon's future remains uncertain, its legacy will forever be etched on the face of our planet. From the tides that ebb and flow along our coastlines to the length of our days and the stability of our planet's axial tilt, the moon's influence is woven into the very fabric of Earth's existence. It is a legacy that speaks of a profound interconnectedness, a reminder that we are part of a larger cosmic dance, our fates intertwined with the celestial bodies that share our corner of the universe. The moon's slow farewell is not an ending but rather a transition, a new chapter in the ongoing story of the Earth-Moon system. As we continue to study this celestial dance, we gain a deeper appreciation for the beauty and complexity of our universe, the delicate balance of forces that govern its evolution, and the profound influence these cosmic interactions have on the emergence and evolution of life itself. The moon's journey is a source of endless fascination, inviting us to contemplate our place in the cosmos, to marvel at the intricate workings of the universe and to appreciate the enduring impact that even the most subtle celestial movements can have on the grand tapestry of space and time. It is a story that will continue to unfold for billions of years to come, a celestial legacy passed down through generations, a reminder of the enduring connection between Earth and its celestial companion. As we conclude our exploration of the moon's slow drift away from Earth, we are left with a profound sense of awe and wonder at the intricate workings of our universe. The moon, our celestial companion, has played a far more significant role in shaping our planet than we could have ever imagined. Its gravitational pull, a subtle but persistent force, has sculpted our coastlines, influenced the length of our days, and even played a role in the emergence and evolution of life itself. The moon's story is inextricably linked to our own, a cosmic partnership that has shaped the course of life on Earth. From its fiery birth billions of years ago to its current slow retreat, the moon has been a constant presence in Earth's sky, a silent witness to the unfolding drama of life on our planet. It has inspired countless myths and legends, guided ancient navigators, and served as a beacon of hope and inspiration for artists, poets, and dreamers throughout human history. But beyond its cultural significance, the moon's influence on Earth is deeply embedded in the very fabric of our planet, a testament to the interconnectedness of all things in the cosmos. The tides, that rhythmic dance of our oceans, are a constant reminder of the moon's gravitational pull, a force that shapes coastlines, influences marine ecosystems, and even affects the Earth's rotation. The length of our days, the very rhythm of life on Earth, is gradually lengthening due to the moon's slow but steady retreat. And the stability of our planet's axial tilt, the celestial lean that gives us our seasons, is also influenced by the moon's gravitational presence. The moon's influence extends beyond the physical realm. It has also shaped our understanding of the universe and our place within it. The study of the moon's motion and its influence on Earth has been instrumental in advancing our knowledge of gravity, celestial mechanics, and the evolution of planetary systems. The moon has served as a celestial laboratory, allowing us to test our understanding of physics and astronomy, and its exploration has pushed the boundaries of human ingenuity and technological innovation. While our understanding of the moon has increased dramatically over the centuries, particularly during the era of space exploration, many questions about our celestial neighbor remain unanswered. The moon's origin story, while generally accepted to involve a giant impact early in Earth's history, still holds mysteries that scientists are eager to unravel. The precise details of this impact, the composition of the impactor, and the processes that led to the formation of the moon's unique surface features are all areas of ongoing research. The future of lunar exploration promises to be just as exciting as the pioneering missions of the past. New technologies and innovative mission concepts are being developed that will allow us to study the moon in unprecedented detail. Robotic missions will continue to map the lunar surface, probe its interior, and search for resources that could potentially support future human exploration. The prospect of returning humans to the moon, this time to stay, is no longer a distant dream but a tangible goal within reach. Establishing a permanent human presence on the moon would be a monumental achievement, opening up new frontiers in science, technology, and human exploration. A lunar base could serve as a stepping stone for missions further into our solar system, a platform for conducting astronomical observations, and a testing ground for technologies that could benefit humanity, both on Earth and beyond. As we continue to explore the moon, we will undoubtedly make new discoveries that challenge our assumptions, expand our understanding of the universe, and inspire future generations to reach for the stars. The moon, once a symbol of the unattainable, is now a stepping stone on humanity's journey into the cosmos, a celestial beacon guiding us towards a future filled with possibilities yet to be imagined. The moon's slow drift away from Earth, a celestial ballet unfolding over eons, is a poignant reminder of the impermanence of all things, even in the vastness of space. The universe, as we know it, is in a constant state of flux, with celestial bodies moving, evolving, and interacting in an intricate cosmic dance. The Earth-Moon system, a partnership that has endured for billions of years, is but one chapter in this grand cosmic narrative, a story of interconnectedness, change, and the enduring power of gravity. The Moon's legacy, however, will extend far beyond its eventual departure from Earth's orbit. Its influence on our planet, etched into our coastlines, embedded in our biological rhythms, and woven into the fabric of human culture, will persist long after its glow has faded from our night skies. The tides will continue to ebb and flow, albeit with diminished force, driven by the memory of the Moon's gravitational pull. The length of our days, a testament to the Moon's slowing influence on Earth's rotation, will serve as a subtle reminder of our celestial companion's enduring legacy. The Moon's slow farewell is an invitation to contemplate our place in the cosmos, to marvel at the grandeur and mystery of the universe, and to appreciate the interconnectedness of all things. It reminds us that we are part of something much larger than ourselves, a cosmic tapestry woven from stardust, shaped by gravity, and illuminated by the light of distant stars. As we gaze up at the Moon, let us remember its enduring influence, its celestial dance with our planet, and the countless ways in which it has shaped our world. Let us carry with us the wonder and inspiration that the Moon has evoked in humanity for millennia, and let us continue to explore the cosmos with open minds and a deep appreciation for the intricate beauty and mystery of the universe we inhabit.